Alright, so today we are going to be talking about section 5.8. This is called curve fitting with quadratic models. This entire section is going to seem kind of like review because it's very similar to one that we talked about back in chapter 2 that was curve fitting with linear models. So really all we're going to be doing is we're taking that same concept of trying to fit an equation to a set of data, and instead of looking for a linear equation, we're looking for that quadratic equation. So our goals for today are going to be to use these quadratic functions to model data, and then to actually analyze and predict different things based on those models or those equations that we get. Okay, so first thing we have to decide before we even get to using a quadratic equation is whether a quadratic equation makes sense for a set of data. And so you'll remember back when we talked about linear equations, we talked about making sure that the slope was always the same. We checked our x values and our y values and made sure that those were kind of corresponding with each other, that we weren't getting different values that we didn't expect based on having the same slope. When we get to quadratic, it gets a little more complicated. We actually have kind of two things that we have to check. So the first one is right up here on top. We have to make sure that our x's are equally spaced. If those x's are not equally spaced, then we can't actually do the second part. And that second part is then to look at what we call the differences. And so when we have quadratics, because we have that squared in the equation, we're really looking at what the second difference is. So we're going to take each of our y values, or our f of x values, and we're going to subtract the one on the left minus the one on the right. I'm going to write that right over here. We're going to do the one on the left is being subtracted from the one on the right. I'm sorry, it's kind of hard to read that, but we're subtracting from the one on the right the one on the left. So we start with the one on the left, or on the right, and subtract the one from it. So if we look here on the far right side here, if we're looking right here, I'm taking that 9, I'm subtracting the 4, and I get a 5. Or I subtract the 4 from, or 1 from the 4, and I get a 3, and 0 from 1 gives me 1. I do get negative numbers as well. If I subtract 4 from 1, I get a negative 3. Okay, those numbers that are here in blue are what we call those first differences. That's the first time I subtract the numbers that I get. What we're concerned with, though, because we had that square in the equation, is we want to look here at our second differences. Our second differences are really what we're looking for. If those second differences are all the same number, including the same sign, then we know that we have a quadratic equation. So that's really what we're going to be looking for when I ask you to decide if a set of data is quadratic or not. We're really looking to see, are those second differences the same? And that's really what your explanation would be as well, is yes, the second differences are the same, or no, the second differences were different, or they weren't all the same, they weren't constant. Okay, so let's go ahead and look here at an example. So this is example 1. This one comes right from your notes as well. If we look, we have a set of data here. We got 5 points. We need to decide if this could be represented by a quadratic equation, and we need to explain that as well. So the thing we have to check are those first and second differences. Before I even get there, I have to check and make sure my x values are equally spaced. And if I look here, going from 1 to 3 to 5 to 7 plus to 9, I'm taking and I'm adding a 2 every time here. Okay, so I am going up by the same amount every time. They're equally spaced, so we're good to go there. But let's go ahead and take a look at those first differences. So I'm going to go ahead and take the 1 here, and I'm going to subtract a negative 1. Well, 1 minus a negative 1 is going to give me 2. And if I keep going with that, I would have 7 minus 1 gives me 6, 17 minus 7 gives me 10, and 31 minus 17 gives you 14. And if these numbers are starting to get too big for us, then we can go ahead and use our calculator to get those first differences. Okay? But again, I don't care about the first differences. What I care about are the second differences. So let's go ahead and take a look at those. So here we see our second differences. Again, I'm taking the 6 and I'm subtracting the 2. 6 minus 2 gives me a 4. I can take 10 and subtract the 6 gives me a 4 as well, and 14 minus 10 also gives me 4. So I get that same difference the entire time there. That's a constant second difference, and say that yes, this is in fact quadratic because those second differences are constants for an equally spaced x value. And really this equally spaced x part we don't necessarily need. That's kind of assumed that we're just checking that if we're looking at second differences. Okay? So that's really what I should see when you get to homework. If I'm asking you to determine if something could represent a quadratic, I need to see you finding those second differences and then saying that it is a quadratic function or not based on whether those are constant. Alright, Okay, so now let's go ahead and talk about actually getting the equation. So once we know that we have something that's quadratic, then we can go ahead and look for the equation. Okay, and the way these quadratic equations work is we need 3 points to determine them. Okay, those 3 points are going to allow us to make sure we get just one equation that would fit all 3 of those points. If you remember back for a line or a linear function, all we needed was 2. But now here we're going to need 3. And those 3 points have to be what we call non-collinear. If we look down here at the bottom, we talk about reading math. Collinear points are points that lie on the same line. So non-collinear are ones that do not lie on the same line. So basically, if I had 3 points that all were on a line, I could put a straight line through them. I wouldn't get my curve that I would want for a parabola, which causes an issue. So we just need them to not all lie on the same line, and we'll be good to go. Okay. So once we have those 3 points, and those 3 points don't have to be equally spaced, they're just any points from that equation. And one of those we can go ahead and start to look at our model. So a quadratic model is really just a quadratic equation or function that's going to fit the data the best. Okay, if you remember back in chapter 2, we used this process called linear regression. That was what we used to make predictions and then kind of apply those to kind of make some guesses at kind of prices and different things as we would go up our different amounts. So what we're going to be doing now is doing the same thing, but instead of using a linear equation, we're using a quadratic, and so we call it quadratic regression. And if you think about in our calculator, the way we did this is we used the stat menu. Okay, and then the stat menu, we looked at both the edit and calc pieces. Edit was where we put data in. Calc is where we actually got to the equation. In the calc menu for linear, we use linreg, which stood for linear regression. So this time we're going to have to use something right at the top here called quadreg. I do not have my calculator with me right now, but I believe that is option 5. Okay, you can double check that in yours, but definitely go with quadreg, even if it's not option 5. Just check that it's quadreg. One thing that we're going to find when we do that quadreg is we're going to get this thing that we call r squared. You'll remember back from linear equations we had an r value that we called our correlation coefficient, and that told us how well our model fit our data. Well, now we have basically the same thing, but now it's what we call r squared. R squared is really the same thing. The reason we used r before and not r squared is r also told us something about the slope and kind of the direction of the slope. With quadratic equations, we don't have slope, and so it's actually easier to use an r squared value because then it's going to always be positive. And so you'll see here in this paragraph we say that the closer r squared is to 1, the better we fit our data. Okay? And then the worse it is, the closer we're going to get to 0. Here we won't have any negative r values anymore because again we don't care about the direction anymore. We're just concerned with how well does it fit. So let's go ahead and try this one here quick. So we're going to write a quadratic function that fits these points. Okay, so we have 3 points here. We have 0, -3, 1, 0, and 2, 1. So we're looking for a quadratic equation that's going to go through all of those. Okay. Now, I do have to admit to you, I do not have my calculator with me right now, so you're going to have to do this along with me, and I hope that you get this done. We can check it once I get back tomorrow. But let's go ahead and kind of walk through what you should be doing, and you can do it on your calculator and actually get the exact values as you go. Okay. First thing we need to do here is we have some x's and y's here. I have an x, an x, and an x. And then I have my y, a y, and a y. I need to put those into my calculator. So first thing I'm going to do is go to stat, and then over to edit. Actually, it's the first menu you come to. You're going to enter there. You should see L1 and L2. L1 is for your x values, L2 is for your y values. So once you get that set up, you should see something like L1 and L2. We'll have 0, 1, and 2. And for our y values, we'll have -3, 0, and 1. Okay, so you should get that table set up. Hopefully you're getting that right now. Once you have that finished, you can go ahead and go over to quadreg, and again that's going to be in stat. Then you'll have to arrow over to calc, and then you're looking for that quadreg button. Again, I believe it's option 5. Hopefully you guys can find that one and verify with each other what option it truly is, but I believe it is option 5. And once you have that, you'll have those same options we had with linear regression. Don't mess with any of that, just go all the way down to calculate. Once you do that, you'll get to a screen that has all of your information on it. On that screen, at the very top, you're going to see y equals ax squared plus bx plus c, which hopefully looks familiar to you. This is our standard form where we have a, b, and c. Those a, b, and c should then be listed right below that y value. Okay, if we just plug each of those then back into our equation, that will be our model for our data. Okay, also on the bottom there you should see an r squared value. That again is going to tell you how well it fits. I believe for this one, because we're only using 3 points, it should be a 1. If for some reason it's not, you may have typed in a point incorrectly. Alright, so hopefully you're getting that. If not, we can definitely look at this one tomorrow once I'm back as well. Alright, next we're going to go ahead and look at a story problem. This again is going to be using your calculator. This one I actually have some screenshots of your calculator so I can kind of walk you through a little bit more what it looks like. But a lot of this again is going to have to be done on your own. Okay, so let's look at our scenario here. We have the table below is showing the cost of circular plastic wading pools, kind of the ones that you play in your backyard. A lot of people use them for their dogs or their pets or small kids or whatnot. That's really what we're looking at. Okay, we're trying to find a quadratic model to represent the cost of the pool given its diameter, and we're going to use that model to estimate the cost of a diameter of 8 feet. And you can see right here my table only goes up to 7, so I'm trying to find kind of that 8th one and what that would equal. Okay. If I look here, diameter is the one kind of on top, so these are going to be my x values and my y values. When I go to put them in my table, my diameter will go into L1, my cost will go into L2. And that's really what we need to do next. So I'm going to go ahead and shift to the next slide. I'm going to lose all of the data, but you have it still on your page. You can definitely get that into your calculator. And once we get that into our calculator, we should see something like what we have over here in L1. Again, you can see, or sorry, step 1, you can see we have our two lists, L1 and L2. If you need to clear those out again, go all the way to the top and hit clear. Don't hit delete. Delete gets rid of everything, and then we have to reset your calculator, which is no fun. So just hit clear and get rid of that data, and then you can go from there. Step 2 then is actually doing that quadratic. So again, kind of jumping over. Now you can see right here at the top, this is your equation. This is your y equals ax squared plus bx plus c. That's what you should see on your equation. Then I have my values of a, b, and c that I can all plug into that equation. Okay, and again, we're going to take probably 3 decimal places. That just makes sure that we have enough that when we start to use it, we're not rounding too much. Okay, and if we look at our r squared value on this one, we have 0.9998. That is about as close to 1 as you're going to get without actually it saying 1 for you. Okay, so this is a pretty good estimation of what the cost is going to be based on that diameter. Okay, so when we go to make our prediction, it's going to be a pretty good one. Okay, so let's go ahead and take a look at that next piece. Now that we have the equation, we can plug that into our calculator, or we can actually do the next part by hand. A couple options here. We can either graph it. The problem with graphing it is then we have to adjust our window. We have to then kind of estimate. It's not the best one. I would actually not do graphing, so I'm going to go ahead and cross that one out. What we look at is either the table, which means we have to put that equation into y equals and plug everything in, or if we just want to do it by hand, we know our ax squared plus bx plus c is our full equation with the a, b, and c already plugged in. We know we want a diameter of 8, so that 8 could plug right in for x in our 2x squared in our x piece, and then just simplify it out. It's really up to you if you'd rather plug this entire thing into your calculator and just make your calculator do it, or if you want to plug in each piece and kind of figure it out by hand, still using your calculator of course, but kind of doing it more manually. It's really up to you. Either way, we're going to end up with this row of the table down here, that row for 8, which gives us 49.538. So let's go ahead and talk about with that. So that 49.538 really would round to a 49.54, and that tells us that if I want a diameter pool with 8 feet, so I want a pool that's 8 feet across, that is going to cost me about $50, $49.54. Okay? So that's kind of how we can use that equation, okay, and kind of work through an entire problem in more of a real world scenario. Okay? So that is it for our notes today. You do have homework that should be listed on the back board. If it's not, it should be on the front board as well. So you have that. Go ahead and get started on that. You can use the rest of your time in class to be working on your homework. Hopefully see you tomorrow.